Thank you very much for the great opportunity. I'd like to thank everyone for the Q2B. So I have the opportunity to discuss today the hypersensitive MRI and NMR using quantum technologies. So I belong to QIQB of Osaka University. QIQB stands for Center for Quantum Information and Quantum Biology. I work as a director for that center. We look at not just quantum computing, but also quantum sensing and quantum communication as well. And so we have about more than 30 full-time researchers. So we are actually the largest center in this particular field. And myself, I'm not just working on quantum computing, but other fields as well. Originally, I was focusing on using an nuclear spin for quantum computing. And then we were using machine learning, and there was the largest implementation of that on a world scale back in 2021. And so we are trying to utilize that and build on that result. And so as part of that, we are also involved in software development and control devices as well. And with regard to the control device, it was not just about nuclear spin. It can actually be used for superconduction, and a superconducting qubit is actually an area with a lot of applications. So we are also looking at that as well. And the weekend announced the 64-qubit superconduction system, and I'm proud to have been part of that. Currently at Osaka University, I'm still working on quantum computers, so that we can use them for R&D. And so the superconducting qubit driving equipment we are manufacturing, so that that technology has been transferred to QL Inc. I'm actually a co-founder of QL Inc. And so we are actually trying to start supplying that system. So it's really about utilizing quantum technology to making that available to the wider society in academia as well as in industry. And so the NMR technology, and using this not just for quantum computing but for sensing, is what I'm going to discuss today. So with regard to quantum sensing, actually, there's not a lot of good textbooks out there, but about 2 years ago, I actually supervised this textbook. So anyone who's interested in quantum sensing in general, this is the book for you. And so just reviewing what quantum sensing is. So you will use the quantum state of qubits to sense something. That's what quantum sensing is about. So qubits can be about spins, photons, and atoms. And in the morning, we had a number of presentations to that effect. And so there are various devices we can use for quantum sensing. And that technology can actually be used not just for quantum computing, but there's a lot of technologies in common. And another thing is that it is expected that large-scale quantum computing will only come after a certain time, but these technologies for sensing are already available. And this is a famous quote from Jay Prisco in 2019, and that's when Google announced that they have the quantum supremacy, and the statement is in response to that. So the question is the controlling large-scale quantum systems merely really, really hard, or is it ridiculously hard? And it's either of the two. And in the former case, we might succeed in building large-scale quantum computers within this century. And if it's the latter, it may only take a few decades. So the Google achievement indicated that it's just merely really, really hard, and it's not ridiculously hard, but it's still going to take a number of years, a few years, quote. But then within that few years, quantum technology is expected to bloom. So maybe quantum computing is yet to come, but before that, quantum sensing would actually become pretty much part of society, according to Preskill. And I would really want to have quantum computing and quantum sensing be used wider in society. So I'm particularly focusing on nuclear spin and using them as qubits for nuclear computing, quantum computing. And there was a news about a desktop 1 million yen 2-qubit quantum computer being available commercially. And so I've been involved in that for a long time. Back in 2001, there was this team with IBM myself using 7-qubit, and we were able to do the factorization. So this is really about using an RF magnetic field or electromagnetic field and detecting that. And initially that was used for molecular analysis. And we were looking at that for material and for drug discovery, and it remains the case. And there's about 100 billion yen market. And it's not just about analysis, but the technology is used for medical diagnostic for the imaging. So the RF can actually go into the deeper parts of our body, and it's still widely used. And so including the maintenance or after-sales market, there's this market of about 1 trillion yen. So nuclear spin is actually used widely for sensing already, but there's one shortcoming. The nuclear spin energy is very small, so sensitivity is low as of now. And in relation to that, for quantum computing, the fatal shortcoming is that initialization is quite challenging. And that's because you have this tube inside which there's a sample, and there's a lot of nuclear spin, and they are not aligned. And so there's this competition between thermal energy and nuclear energy, and thermal energy wins. And so polarization shows how aligned or misaligned they are. And so it's the difference between the directional spin and over the number of spins, and it's very small. And so what happens is that those counter directional spins are canceling out each other on a microscopic scope. And so, spin energy, magnetic field, and the inverse of the temperature, those are the factors. So if you have a typical environment, free tessera, room temperature, which would be the typical environment for your MRI, the polarization is 0.001%. So you can only detect 1 in 100,000 nuclear spins. That's the level we are at now. So there has been research trying to improve the sensitivity for a long time. And one core technology is DNP, dynamic nuclear polarization. So this is about including nuclear polarization from the thermal equilibrium by irradiating microwave so that the electron spin polarization is transferred to nuclear polarization. And so the electron polarization is actually higher by 660 times, and that's how you would enhance the nuclear polarization. And so if you go down to 1.1 Kelvin, then you can actually get the alignment of the electrons, and then you irradiate your microwave, a sub-millimeter wave that is, and then it's 1.1 Kelvin, so obviously everything is in solid form. And then you would actually apply hot water, and then the sample and the solution will come to room temperature. And then you will polarize and do an injection. So that's a dissolution DNP, and that was a great breakthrough. But so we were able to maintain a polarization of 10%. That's up 100,000x, or rather 10,000x. But then the nuclear spin is actually only good for 20 seconds. But then you have that 20 seconds to inject into a test tube or inject into a body. And so that's what we are using now, so for drug discovery or material analysis or medical diagnostic. And so that was in 2003 that the dissolution DNP came out. And since then, immediately in 2006, metabolic imaging was successfully conducted. And again, that was revolutionary. Usually, when you have MRI, you have black and white images, and that only indicates where water is concentrated in. And so sensitivity is low. And so, 60% is water in your human body. But then if you have the enhanced sensitivity by 10K, then you can actually look at a drug, for example, at concentration that's lower by 10K, a factor of 10K. And so, for example, if you use a pyruvate and you have the spin aligned and then inject it into your body, you can actually monitor how that pyruvate extends or diffuses into your body, and that will be actually metabolized into lactates and alanines, and you can actually monitor that. So in your healthy cells, what is not metabolized into or not metabolized into lactate, you can see. And so in 2007, there was this idea looking at using this technology to look at tumor response to treatment. And you can monitor the metabolization in real time. In the past, you will have to wait until the tumor is smaller. But then with this technology, you can actually monitor as you're injecting the drug. And then that was, again, a good breakthrough, and we went into clinical study. And now in the United States, you can actually almost get that in hospitals. It's almost ready. So in a short time, you'll be able to receive that treatment. So aligning those nuclear spins or hyperpolarizing them and injecting the drug, you can actually look at the efficacy or efficiency of your anti-cancer treatment. But then, if you really want that treatment to really become widespread and available, we would want to use the quantum technology, because what we're doing now is you need to get a cryocooler and cool everything to a very low temperature, and then transfer the electron polarization to the nuclei, and that would mean you have a great big instrument, and we are trying to realize that in room temperature. So we're trying to use the laser so that the spin can be aligned regardless of the temperature. And if this is successful, that can really reduce the form factor as well as the cost factor. So the technology is based on this physical mechanism. So we have this pentacene. This is a pi conjugate system, and organic. And so if you use a laser to excite that, it will go to a triplet state. And so this is a polarized state. And so the electron orbits and the spins of the electrons, there it will be this coupling, and it's this selective phenomena happening. And at that right moment, you can actually transfer that spin to the nuclei. And so DNP was realized at low temperature 70 years ago. And then another research actually led to the use of pentacene, and there was a successful single detection of pentacene magnetic resonance. And then the same team actually was successful in using pentacene for DNP. This is the same team in the Netherlands. And then that was realized by another team, this time using NV, and that was 1997. And 9, we have the diamond sensing using NV sensors, and it's also used as a readout for quantum computers. And so DNP using pentacene was transferred into Japan, and Kyoto University realized the polarity of 34% at 77K. And then the DNP using NV centers was also researched, and this team in Israel realized 5% at room temperature. And then our team realized 34% using pentacene at room temperature. And so I named this technology as room temperature hyperpolarization and started research so that this can be applied in the real world. So the system looks like this. We have the microwave and optics. And so we will irradiate laser, and then the pentacene in the sample will be excited, and then the electron spin will happen. And then the host molecules, a lot of them are here, and we want the host nuclei to get the spins. So first the closer nuclei will have that spin transferred, and then over time that will also propagate to others. And then you repeat that over time, maybe tens of thousands of times, so that the overall sample spin alignment happens. But then we have to think about relaxation time, so there's a balance, and the balance will actually limit the final attainable polarization. And that's what we did, and that was with solids. And then in 2018, we were successful to actually realize this in liquid form. So that was dissolution DNP at room temperature. So until halfway through, it's actually in solid state. And then at one point in time, you will actually use hot water to dissolve the samples, and then you can see how there's a transition to liquid state happens. And that was in 2018. And then we were involved in the nationally funded project, which is QLEAP, and Group B is about quantum and life science cross-section. And so we are working with a number of team members on the applications. So first, we looked at not just pentacene, but we also tried to realize DNP with NV centers. So the same instrument can actually successfully use either pentacene or NV centers. And then we also now have this NMR spectroscopy sensitivity enhanced. And so we are trying to use that to detect the protein-ligand interaction, and we are again successful. So we have those triangular molecules which are hyperpolarized at room temperature, and that will be bound to the protein. And you can see how the shift of the curve happens and how the broadening happens with enhanced concentration. And if we can use this, this can be useful for drug screening. And so currently, when we are using NMR for drug screening, this is the basic thing you do, as you can see in the screen, but we are successful in realizing that at room temperature. So we have this polarized molecule, which is the in triangle, and that will, and then when there is the presence of a target drug, then that drug will displace this weak binder, and we can trace whether that happens or not, because a strong binder to a protein is usually usable as a drug. And so, for example, we looked at warfarin, which is an anticoagulant. And we actually made it compete against the hyperpolarized salicylic acid. And you can see that there's the change with the warfarin. The curve changes, and so this actually allows us to detect strong binding. And this is a known drug, obviously, but we can use this for unknown target, and we can actually efficientize the process of drug screening. So I think the first step has been successfully made. And this has been published on the 4th of this month of July. And we have some challenges still. We obviously want to use it for various molecules, and they had been difficult, but we have a lot of research happening out there. And Tokushima University and Kyushu University have come up with various means to extend it to different molecules, such as water, erythritol, and succinic acid. And then we are also working on the MRI. This is at this Suita campus of the Medical School of Osaka University. So next to the MRI system, we have this DNP. And so we have this room temperature hyperpolarization system connected to the MRI. So we have actually been able to do that. So we would like to use the imaging of the metabolism so that we can use it for anti-cancer drug research. And so the summary is that we talked about quantum sensing and hyperpolarization of nuclear spin and how it's used in cancer diagnostics, and room temperature hyperpolarization allowing drug screening. Thank you very much for your kind attention.